Given that x equals sine over cos y, use the quotient rule to show dx dy is equal to sec squared y. Given that tan y equals x minus 1, use a trig identity to show that sec squared y equals x squared minus 2x plus 2. Show that if y equals arctan of x minus 1, then dy dx equals 1 over x squared minus 2x plus 2. Part D. The curve has an equation here. Find the value of the x-coordinate of each of the stationary points of the curve. Find the second derivative. Hence show that the curve has a minimum point, which lies on the x-axis. So that's the question then. Let's have a little look at it. I've got it in summary form here. So the first thing is use the quotient rule here for x equals sine y over cos y to get dx dy. So x equals sine y over cosine y. So dx dy then. Use the quotient rule, so it's v times du dy. Sine differentiates to cos. So the symbol is y, the derivative with respect to is y. So it's v du dx minus u sine y over dv. Cos differentiates to minus sine, so that will be plus. Be another sine all over v squared, which is cos squared. So that tells us then dx dy is equal to cos squared plus sine squared is 1 over cos squared y, and that's sec squared y, isn't it? Which is what we wanted to show. So that's part A. Okay, given that tan y equals x minus 1, use a trig identity to show that sec squared y equals this. Okay, so let's square it, and then we'll use the trig identity. So part B, so tan of y, wasn't it, is equal to x minus 1. So that tells us then that tan squared, square both sides, is equal to x minus 1 squared, which is equal to x squared minus 2x plus 1 when we square the bracket. Now sine squared plus cos squared equals 1, so the tan squared divided by cos is tan squared plus 1 is equal to, divide by cos all the way through, sec squared. So there's our little memory aid for trig identities. So we can replace tan squared by sec squared minus 1. And that will equal x squared minus 2x plus 1. And move the 1 over, so we end up with sec squared y is equal to x squared minus 2x plus, move the 1 over, 1 plus 1 is 2. That's what we wanted to show, wasn't it? Here. So that's good. That's part B. So we've done that. Show that if y is equal to arc tan x minus 1, then dy dx is equal to that. So we want dy dx from this, part C. So y is equal to arc tan, or inverse tan, of x. We want dy dx. Just trying to remember the x minus 1. Remember the question, does help. And then we want dy dx. So let's have a look at this then. Okay, so dy dx here. Tan differentiates to 1 over 1 plus x squared, so it's 1 over 1 plus x squared, but this time it's a function of a function, so it's the something squared multiplied by the something differentiated, which is 1. So that's equal to then, it's going to be 1 over, expand this bracket, we get x squared minus 2x, so 1 here and then there's 1 there, so it's plus 2. So that's dy dx then. And let's have a look at the question, that's what we wanted to show. Part D, y equals tan to the minus 1 of x minus 1 minus log x. Find the x coordinates of the stationary points. So, part D, y equals tan to the minus 1 of x minus 1 minus ln x. If I remember right, let's have a look at that, just to be sure. Yep, find the x-coordinate of the stationary points. So we need dy dx is equal to, now we've differentiated this already and we got this, so that's presumably what they want us to use. And then the log differentiates to 1 over x. So let's cross multiply then, the x comes up here. And these more than one term, put a bracket with a minus around it, so there's a minus this lot. All over the x squared minus 2x plus 2. So that's equal to, well here we've just got simply x squared minus x squared. We've got plus 2x plus another x is plus 3x. And then we've got a minus 2. All over this thing here, x squared minus 2x plus 2. So what have we got then? We've got a minus bracket x squared minus 3x. I've taken the minus x, it's easier to look at it like that. And then that's x squared minus 2x plus 2. So that's dy dx. Now we can factorize the quadratic, because it's in user-friendly form here. 2 ones with a minus 2 and a minus 1, isn't it? Minus 2, x minus 1. That will give us x squared. Minus x minus 2x is minus 3x plus the 2 over the x squared minus 2x plus 2. So let that equal 0 then. It implies x is equal to 1, x is equal to 2. Two solutions. And I think it was the x coordinates, wasn't it, of the stationary values is all we were asked to find. Okay, so that's that done. Find d2y by dx squared now and show it's a minimum on there is a minimum on the x-axis. So the second derivative now. So we've got our first derivative, which is here. Now, or it's here. So I'm going to treat it as this is the derivative because it looks like it's easier to deal with than this. Although, no, I'm happy to deal with this. So part 2, d2y by dx squared is equal to, well, this is a function, something to the minus 1 will be minus something to the minus 2 squared then, multiplied by the something differentiated, and this differentiates to 2x minus 2. So we've got that, and then, so that's that done, so it's something to the minus 1 is minus the something to the minus 2, multiplied by the something differentiated, function rule, and here we've got the minus 1 power, which is what we've got, comes to be with that minus to make a plus, 1 over x to the minus 2, so we can write 1 over x squared, can't we? So there's the second derivative, which we can tidy up just a bit, so we've got 2 minus 2x on top, over the x squared minus 2x plus 2, all squared plus 1 over x squared. Now that was part 2, that was the second derivative. Show that it's a minimum, show min is on x-axis, show that it is a minimum and it's on the x-axis. One of these is a minimum, so when x is, okay, so which one are we going to take? So I'm going to scratch this little section and work just above now. Okay, so we got that, and x equals 1, x equals 2, pen. d2y by dx squared then is equal to, okay, so here, this is squared, so it's positive. So when x is 1, this will be 0. Plus 1 is positive, so a minimum. When x is 2, this will be negative. So d2y by dx squared then is negative when, well, the only possibility, because this is always positive, this bottom bit's always positive, it's only when this is negative. That's the only possibility. So that would be when x, so try x equals 2. So let's try that then. d2y by dx squared then. Put 2 in. We get 2 minus 4 is minus 2 over 2 squared is 4 minus 4 is 0 plus 2, which is squared, so that's 4, plus 1 over 2 squared, which is 1 over 4. So that's equal to minus 1/4. So max at, oh, it's negative, and we want a minimum, don't we? When x is 1. Min is on x-axis, so we want it when it's negative. So we want to change that now, and I should have said is positive, which is better anyway, because all the terms are positive now and there's no checking needed. When this is positive, so we try x equals 1 then, and this would be greater than or equal to 0. So try x equals 1, that's better, because the expression works now. Everything fits now, doesn't it? Because when x is 1, this will be 0, but this will be positive, and we'll have a minimum. When x was 2, it's negative. So that all we need to worry about is the positive, so let's just try that then. So d2y by dx squared then, when x is 1, this is 0, so all of this is 0. 1 over 1 squared is 1. So a min at x equals 1. Here, we need the y value to show it's on the x-axis, don't we? Y is equal to then, when x is 1, so part D, arctan of 0 minus log 1. Tan to the minus 1 of 0 minus log of 1 is equal to 0. So that completes the problem.